Hello, Chem 115 students. More delayed than expected, but I'm trying to provide you some extra help on balancing equations and working on mole ratios. I'm having some ridiculous technical difficulties. I will have to do the best I can to make this work for you. We're going to talk about how chemical reactions are written, and we won't talk about classifying reactions for the time being. So how to figure out how to write a balanced chemical equation properly. To write a chemical equation, you have to determine the correct formulas for the substances involved. That is key step number one. Without that, you are never going to get it right. So get the formulas right, otherwise the whole equation makes no sense. Remember, we covered these things a while back when we were talking about ionic and molecular compounds. We sometimes forget about them in the intervening chapter. So don't forget about that. You'll look at this statement and determine which things are reactants, which are products. The reactants will always be on the left side of the arrow. The products will be on the right. And so let's try an example here. And this is going to be very substandard because I'm not using my usual tool today. But for writing for the formation of aluminum bromide from elemental aluminum and bromine. So the formation of aluminum bromide, that would be your product. So aluminum with bromide is going to be on the right side as a product. The formula is the first thing you have to figure out. Aluminum with bromine, well, think about the ions that would be included. So aluminum as an ion is going to be a +3 ion because it's in group 3 or 13, 3A or 13. The bromide ion is going to be a -1 ion. If you think about that for a few seconds, I hope it becomes clear that you should have 3 bromide ions for each aluminum. From tells us what the reactants were. So elemental aluminum is simply aluminum as a solid. It's just exactly what you pull off the roll in the box when you're using it in the kitchen. Same thing, that's aluminum. And then with bromine, bromine is one of those unusual elements which happens to occur as a liquid, but in addition to that, it is going to be diatomic, as are all the halogens. So list that as Br2. Make sure you always get the formulas correct for things like bromine and an ionic product. And bromine is a liquid. That isn't key to balancing the equation at this time, but we'll at least describe it for the moment. Now, figure it out. What do you have to do to get the right side and left side to have the same number of atoms? Well, we've got 3 bromine on the right, 2 on the left. The only way to do that is to multiply the left side by 3, or at least the simplest one, and the right side by 2. That means you all of a sudden have more aluminum on the product side than you do on the reactant side. So you go back and add 2 on the left side, and now you have 2 aluminum atoms on each side, and one is an atom, one's an ion, and 6 bromines on the left and 6 bromines on the right. That is now balanced. Now, just as I did on the previous slide, to balance things you will use coefficients. Usually we like to use whole numbers. There are occasions when you don't, but normally that's the preferred one. And the simplest whole number ratios are ideal. We never change the subscripts. Leave the formulas alone. You start with the elements that appear in only one compound or formula on each side of the equation. That's usually easier. Leave for last the elements that exist in elemental forms, so they're going to be easier, and go from there. You just have to be careful that you've checked everything when you're done. One of the easiest things in simplifying your work with these is when you have polyatomic ions. You may handle them as a group if they do not change from start to finish in the reaction. Commonly that will be the way you will run into them. Sometimes there will be exceptions, but most of the time our polyatomic ions can be handled and counted as entire groups. So to make sure you remember what you're doing, to figure out the total number of atoms, you multiply a coefficient times a subscript to get there. So we did that with the aluminum bromide example. Let's not do it twice. Making sure the balanced equation is what I did when I was talking it through for you. So I checked left and right to make sure you had the same number of atoms as reactants as we did for products. If it looks balanced, double check. That's always wise. And then ideally we will reduce coefficients to lowest whole number values. We don't need to have multiples of 2 or 3 in things. So let's try some other examples. Other examples. Well, these are already provided with chemical formulas for you, so you don't have to get them correct. So chlorine combining with hydrogen to make HCl. there's 2 chlorine on the left, well then you'd have to have more on the right. So put in a coefficient, and now that makes it there's going to be 2 hydrogens as well, but that's still consistent with what's on the left. That equation looks straightforward to balance. The next one, potassium reacting with bromine to make potassium bromide. Remember how to name compounds. Potassium as the element and bromine as an element can combine that way, and we'll talk about that more in the next chapter, chapter 5. In order for there to be 2 bromine on the left, you kind of have to have 2 bromine used in the product as well. In order to make that balance, we put a 2 in front of KBr, potassium bromide. And again, you'll have to balance that out by putting 2 in front of potassium on the left. So now you have 2 potassium on both sides of the arrow and 2 bromine on each side. That one's good to go. Next example, calcium hydroxide with HCl. We would form calcium chloride and water. So let's just work our way from the left across until we figure out what needs to be changed. Calcium so far looks fine. There's 1 of each, 1 on each side. Hydroxide, let's leave that for a minute till you can tell where it's going, but in at the preview thought here, hydroxide is going to combine with hydrogen to make water. And that's a good thing to notice because there's a number of examples where that will happen. So we can think of it as being combined in 1 hydroxide with 1 hydrogen. Now, I'll continue for a minute, we'll come back to it. So the hydrogen on the left looks like 1, but there's also some in hydroxide, so let's pause, but do chlorine first. This will come out simpler for the time being. Chlorine on the left is just 1, chlorine on the right is 2, so we'll need to have 2 chlorine on the left. So stick in a 2 as a coefficient. Now what happens? We have to consider what to do with hydrogen and hydroxide. Well, you've got 2 hydrogens and 2 hydroxides, so you should make 2 hydrogen hydroxide, otherwise known as water. If you look that over, we still have the calcium balanced with 1 each. Hydroxide, there's 2 on the left and 2 on the right. The hydrogen ion was combining with it in making water, so there's 2 on the left and 2 on the right. Chloride, 2 on the left, 2 on the right. That should be all balanced. Okay, do another one. Potassium hydroxide with sulfuric acid, H2SO4, making potassium sulfate and water. So here's an example of some polyatomic ions that do not change. Sulfate is SO4 with a -2 charge. Sulfate still looks like sulfate when it's done. Those are already fine. Don't work too hard to fix them. If they look pretty good, we probably can leave them as is. So starting on the left, potassium on the left side of the arrow has just 1, on the right side of the arrow has 2, so we better find some to put on the left side, otherwise we've created matter by putting 2 on the right side. 2 potassium now balances with 2 potassium on the right when you have it in front of KOH. Now you have 2 hydroxide, and you're going to combine hydroxide with hydrogen again to make water, HOH, hydrogen hydroxide. So if you have 2 hydroxides and 2 hydrogens, that means you'll make 2 water molecules again. So far so good. Sulfate, there's 1 on the left, 1 on the right, nothing more to know. So as long as you can follow the thought that you have 2 hydroxides combining with 2 hydrogen ions to make water twice, that should look balanced to you. Take a stare at it longer if need be. Okay, last one. This is a combustion reaction where you're burning something in air. And this case would be a 3-carbon compound called propane. You've probably seen it in a gas grill. And the products are always going to be water and carbon dioxide when you have a combustion process. Starting from the left, we have 3 carbons on the left side. Well, there's not nearly that yet on the right, so let's put in a 3 in front of carbon dioxide. That must be the fate of the carbon. And on the left, we have 8 hydrogens. On the right, there's only 2 in water, so we'll need to multiply that 2 times 4 to make a total of 8. So far, so good. Now, oxygen is always more exciting in these reactions. On the left, we have 2, which is not very many, but look on the right, we have 4 oxygens in water, plus 3 times 2 in the CO2. And so 3 times 2 is 6, plus 4 is a total of, wow, whoops, wait a minute, that's supposed to be 2. Cross that out. That should be 2. 3 times 2 is 6 instead of 3 times 6. And the sum is 10. And so 10 oxygen on the right, 2 on the left. The only way you can take pairs of oxygen atoms and add it up to 10, the simplest one is just to put a 5 in front of here and call it 5 oxygens. Amazingly enough, this should be finished. So the carbons were 3 on each side, the hydrogen was 8 on each side, and there was 10 oxygens on the left, 10 on the right. Looked funny, but it doesn't come out so bad after all. All right, so here's a couple reminders. These are out of the textbook, but don't forget to take note of them. If you have 1 sulfate on the left side of an equation and you have 1 sulfate on the right side of the equation, you don't have to count out sulfurs and oxygens separately. It makes your life much simpler. In this equation, you have 2 sodium on the left and 2 sodium on the right, and then you're going to do the hydrogen with hydroxide in this example also to make water. This one turns out to be balanced quite easily. So another way of looking at it is down below here. We have 4 hydrogens with 2 hydrogens in the H2SO4 and 2 times the hydrogen there for a total of 4. And 2 oxygens are right here, only in the hydroxide. You can count them up on the right as well and see that you have 4 hydrogens and 2 oxygens. There's more than one way to look at some of these things and you'll still come out fine. Just pay attention to make sure all the parts look right and double check to be sure. All right, here's another one. Let's see if this reaction is balanced, and if it's not, what should we do to make it balanced? In this particular example, we have sodium hydrogen carbonate, also known as what's in baking soda. And if you heat it up, and this is something like what you get to do in lab this week, similar, you'll make sodium carbonate, water, and carbon dioxide. Well, let's start counting and see whether things are balanced. I see a 2 on sodium carbonate on the right. The formula is given, so you didn't have to figure it out. The reason that it's 2 is because sodium is a single plus cation, and carbonate is a -2 anion, so it requires 2 sodium ions to go with it. Apparently we are not balanced yet, so we will have to add some coefficients to figure this one out. We would have to have 2 in front of the sodium hydrogen carbonate. Well, maybe I could put it in here. And make that sodium balance. Now we have 2 hydrogens. How many hydrogens do we have on the right? Looks like 2. So far, so good. And we have carbonate. Well, let's figure this one out. Well, let's see. We have 2 carbonate, but on the right we have something else going on. Uh-oh, let's check this out. So 2 CO3s, but on the right there's only 1 that looks like carbonate. And then there's CO2, and water must be the fate of the other oxygen. So if you have 2 CO3s on the left and you on the right side, you turn it into 1 CO3 carbonate with sodium and 1 CO2. You only have to account for 1 more oxygen to add up to the second carbonate. And that second oxygen is, in fact, the last oxygen, sorry, is in water. Amazingly enough, that does balance out. Let's look at it another way. There are 2 carbons on the left, and there are 2 carbons on the right, 1 in CO3 and 1 in CO2. On the left side, we have a total of 2 times 3 oxygens. And that would be a total of 6 oxygen. Count them up on the right, and you'll see that you have, there's going to be 3 in the carbonate, and 1 in water, and 2 more in carbon dioxide for a total of 6 as well. So there's more than one way to look at these things and still come up with a correct answer. Just make sure you've double checked yourself to verify that it's good. All right, here's some other fun ones. Folks don't always like these picture diagrams, but they're excellent practice. In this diagram, A is red, so it's color-coded that way, and B is blue. We're going to write a balanced equation and figure out, for starters, how to write the formulas correctly. So A atoms are occurring individually, and B atoms are occurring in pairs. So B is going to be represented as a diatomic substance, B2. And so you're going to have A reacting with B2 to make whatever else is happening over here. Well, what's it look like on the product side? This looks like 2 of each. So I could be arbitrary and list A first. That sounds good. A2 and B2 are in your funny looking things. Looks like caterpillars on the right. And so let's figure out how we're going to put that together to make a balanced equation. So we have A and B2 reacting to make A2 and B2. What does it take to get this balanced? It doesn't take too much if you look at it, because B2 is already good. And so all we have to do is add a 2 in front of A, and now the A's are also balanced. So again, this is a case of making sure that your formulas are correct before you start trying to put in coefficients to balance an equation. Oh, there you go. All right, now one other conversation I wanted to have was about mole ratios, the thing we ended up with in the activity 19 in class. When we're talking about balanced equations, we can use these coefficients to represent either moles or molecules, and we discovered that there are occasions where describing them as molecules doesn't make sense because you can't have fractions of a molecule, but you can certainly have fractions of a mole because a mole is huge. So we will think about how things occur in a balanced chemical equation in terms of the numbers of moles of reactants and products, and we're going to use these things as conversion factors quite easily once you see where they are, to figure out how many reactants go with how many products. So looking at the balanced equation and the coefficients that are used in here for this one that's already balanced for you, for hydrogen reacting with nitrogen to make ammonia, it shows that there are 3 moles of hydrogen to produce 2 moles of ammonia, or you could say that 1 mole of nitrogen produces 2 moles of ammonia. These are described as mole ratios because you're just thinking in terms of moles of each substance. So from that same example, there are several other relationships you can use, and you can use these right side up and upside down depending upon the circumstance, always in the fashion that you need to allow something to cancel out in conversion problems. So you can say 3 moles of hydrogen reacts with 1 mole of nitrogen in this first ratio, or you can say that 3 moles of hydrogen are required to make 2 moles of ammonia from the balanced equation. Or you could say that 2 moles of ammonia result when 1 mole of nitrogen is used. Any of these things are equally useful when you're doing these kinds of problems. All right, one more example. A is red, B is blue, but now we have different molecules. This time A is diatomic, so we'll call it A2. And B is also diatomic, and so we always have to get the formulas correct. The reaction now has something interesting in the products. Let's see, A is red, so A has 3 B's with it when you're done. And so call it AB3. And again, making sure these are correct is always key to begin. And so the balanced reaction is going to have A2 on the left and B2 on the left and B3A, or however you wish to state it. I put it backwards here. And now we need to add in some numbers to balance it. And so in order to get this to balance, you're going to have 2 on the right to go with your, to make enough A's. So there are 2A on each side. And then B2 has 3, oops, nope, now we have up to 6. Oh, 6 on the right. So that means we'll have to make 6 on the left as well. So put a 3 here. And now that should look balanced, I hope. Now, how do we use a mole ratio? So what we're going to ask in this particular case is how many moles of product can be made from a mole of A2. Start with your 1 mole of A2, and then we will set up a mole ratio and do it always to be sure that the units are going to cancel where we need them to. And so let's see, how many moles of A2 goes on the bottom to correspond to moles of product. And the product is AB3 or B3A, however you wish to describe it, doesn't matter. It's arbitrary for this particular example. So let's list it as AB3, I like it better. And now go back to your balanced equation. How many moles of A2 are shown in the balanced equation? Looks like just 1. How many moles of AB3? Looks like 2. So you're going to get your answer is simple multiplication. You can cancel out the moles of A2 the way it's set up, if it's set up correctly, and it shouldn't be any surprise that you're going to get 2 moles of AB3 from 1 mole of A2. Well, that's exactly what this equation looks like. So far, so good. Now, second example on this slide then asks us to determine how many moles of product do you get from 1 mole of B2. So instead of writing it again, I'll just write it here, and 1 mole of B2, and then we'll put a mole ratio to correspond here. So moles of B2 have to go on the bottom, and then we'll relate to moles of the product on the top again. That's what we're after. The product is again AB3. And so moles of AB3, we'll put the numbers in corresponding to the balanced equation. Nothing harder than that. And so back to the balanced equation, it says 2 moles of AB3, and it had 3 moles of B2. And so the answer then you will get, after you cancel out moles of B2, is going to be 2/3, or 0.667, however you wish to state it. 2/3 looks fine today. 2/3 of a mole of product, the AB3, for that amount, 1 mole of B2. So this is how we use mole ratios when we're trying to relate amounts of reactants and products to one another, but key always will be that balanced equation that we will use to come up with correct ratios between reactants and products in terms of moles. All right, the next ones I will leave for you to do on your own, since these are posted on Blackboard in the answers to exercises from your chem activity book. You can find these there. Good luck with your assignment. I hope that it helps a little bit.